Hi guys, this video covers doing the binary search tree search operation in an iterative way, meaning using a loop. The previous video described how to do this using recursion. Now we're going to look at how we could do this using a loop. Here's that same slide from that video. This recaps the binary search tree invariant. Remember, as usual, that the invariant says that if I've got a parent node, all of the keys in the left subtree have to be strictly less than the parent's key, and all of the keys in the right subtree have to be strictly greater than the parent's key, like the 61 example over here. And that gives us a way to design an efficient search algorithm. If we're looking for Q and I've got a pointer to a node called where, then if Q is equal to where's key, we found it and we're done. If Q is less than where's key, we need to search leftwards. And if Q is greater than where's key, we need to search rightwards, and that's it. And as promised, we're now seeing the iterative way of doing this. We saw the recursive way in the previous video. Back when we described this as an abstract algorithm, we gave you this pseudocode, and this kind of still applies. We're going to implement this in C++ code now. So the pseudocode says where starts at the root. So to begin with, start at the root node. While where is not null, then we keep looking. Note incidentally that if the tree is empty, then where would be root, and the while loop would stop immediately and go straight down to the throw exception at the bottom. So if this while loop stops, that means that the search failed, and then the next thing that the function does is throw an exception to say search failed. But if the loop runs, then where is not null, so we're looking at a node, and if the key we're looking for is less than the where's key, then where is reassigned to where's left. So go down one level to the left. If key is too big, then we go down one level to the right. And otherwise, by process of elimination, we know that key is equal to where's key. We don't need to check that key is equal because if a comparison is not less than and it's not greater than, by process of elimination, it has to be equal. So at that point, we know we have a successful search and we return the pair in that node. So now we're going to turn this into code. Here's what that could look like. Just to kind of mirror what we had in the recursive code, I have a public function that calls find iterative. This is just so that there's this kind of two functions, find iterative and find recursive, that work the same way. And find iterative is given the query that we're searching for. That's a key. Over here, we've got find iterative. So it's given the query we're looking for, and it returns a reference to a matching pair if it can find that, or it throws an exception if there is no such pair. So I've got a shared pointer to a node called where that's initialized to start at the root. As long as that is true, meaning as long as that's a non-null pointer, then we have that logic from before. If the key we're looking for is less than where's key, where is reassigned to become where's left. Otherwise, if the key is greater than where's key, where is reassigned to be keys right. And otherwise, we know that they're equal, so that's where we return where's contents. That stops the loop. The return statement there stops the while loop and the whole function. That's the success situation where the search succeeded. And if we get all the way through the while loop, then that's because where became null because we went down off the bottom of the tree, and we know for sure that key, the query key, is not in the tree, so we throw a range error in that case. Let's just go through the same kind of examples. Let's say I search for 83. So where would start out pointing at 37. That's a non-null pointer, so the while loop runs, and key is greater than where's key, so where gets reassigned to point at 61, and then the loop repeats again. And then we make the same kind of decision. How does key compare to where's key, which is 61 now? Well, I'm looking for 83. It's greater than, so we'd go right again. Then the loop repeats a third time, and we know we're in this third case, so we would return the pair containing 83. It's a successful search. Let's say we do the 57 example. So the same kind of thing happens. Where is initialized to point to 37, and the loop iterates. We would be in the greater than case, so where gets reassigned to point at 61. The loop repeats again. 57 is less than 61, so this first if is triggered, and where is reassigned to point at 55. Loop repeats again, and key is greater, so we're in the else case down here, the else if case, and we would go right. And 55 is a leaf node, so 55's right pointer is null, so where is reassigned to null, and then this loop stops, and we go down here and throw an exception, and that's the right thing to do because 57 is not in the tree. Let's make a few observations about this. Obviously, this uses a loop instead of recursion. So a lot of the logic in here is the same as what we had in the recursive function. There's repeat until we become null kind of thing, and once the pointer is null, throw an exception. That's like the first base case in the recursive code. And we have the three other cases, less than, equal, and greater. In the case of equal, we immediately return and don't keep repeating. In the case of less than or greater than, we do keep repeating. So all of that same logic is here. One difference, though, is that the code here has to have a while loop. Of course, the recursive code did not have a while loop because it was using recursion to repeat things. So in one way, this is maybe a little bit more complicated because it has a loop in it. The other recursive function only had if statements. Another change is that we need an explicit variable to keep track of the state of the search. So we need to create this where variable. That was not in the recursive code. And we need to update it. Where changes over time. And that adds a little bit of complexity in a way because there's one more variable in the mix that gets reassigned. When you run this, you have to think in your head, what is where right now? Where is representing where we are, which node we're at. So again, a little bit more complicated because of that. The same thing will happen when we get to traversals. We're going to see how to do in-order, pre-order, post-order traversal both recursively and iteratively. And the same thing happens there too, that the recursive approach doesn't need any extra variables to keep track of what's happening. This tracking is kind of done for us by the control stack of which recursive function we're in. But with the traversals, we'll need an extra data structure to keep track of how far along the traversal has progressed, and that makes those a little bit more complicated. So that's just a preview of what we're going to get to in a couple of videos. I would say this is arguably less elegant than the recursive version. Elegant is a bit subjective, but it just doesn't read quite as closely to the definition of the search algorithm to me. That recursive algorithm, when you just read it top to bottom, it pretty much sounded like the definition of how binary search tree search works with the 4 cases. Here, the 3 cases are here. The 4th case is how the loop ends. There's this extra where variable that changes. There's a while loop. So, I mean, it's not bad, but I don't think it's quite as clean and pretty as the recursive code. But both work. They both work, and I can't knock either one of them. They both have the same asymptotic runtime, big O of h, proportional to the height of the tree. So they're both viable alternatives.